Hi, this is Sonia Doucette. In this video, I'll show you how to determine the amount of energy produced during a neutron-induced nuclear fission reaction when mass is converted to energy. This problem says how much energy is produced by neutron-induced nuclear fission of uranium-235 when it produces tellurium-137 and zirconium-97. And the nuclide masses for all of those nuclides are shown there. So what you're doing here is you're finding the mass lost, and then you're using the E equals mc squared equation to plug in that mass term for m and then find the energy, which is E. And that energy is a conversion from mass to energy, which is something that's unique to nuclear chemistry. First, you need to write the nuclear reaction equation for this fission. So what's happening is the uranium nuclide, and I'm going to write it in this format for writing the equations, is bombarded with one neutron, which is written like that, and it gives 137 tellurium. Tellurium has 52 protons, and it gives 97 zirconium, which has 40 protons. So what you want to do here is figure out the rest of the products, because that's not all. And what you really want to do here is account for the number of neutrons. So remember this format where you had X representing your chemical symbol, A representing your mass number, which is the number of protons plus neutrons, and Z representing your atomic number, which is the number of protons. So what you need to do to find the number of neutrons is subtract Z from A. So that's what I'm going to do for all of these elements. So the number of neutrons in the uranium-235 is 143, and of course the neutron contains one neutron because it is a neutron. And together you have 144 neutrons in the reactants. Tellurium, if you subtract 52 from 137, you get 85 neutrons, and zirconium has 57 neutrons. So in total, you can see so far your products have together 142 neutrons. So you're 2 neutrons short. There are 2 more neutrons in your reactant than in your products. So what you want to do is add 2 neutrons to balance that out. So you're basically balancing the neutrons here. So that is your completely balanced equation for neutron-induced nuclear fission of uranium-235 when it goes to tellurium and zirconium. So now what you want to do is you want to find the mass loss by adding up the mass of the reactants and the mass of the products, and then you want to plug that mass loss into the E equals mc squared equation. So let's first do the mass of the reactants. Uranium-235, or given the mass, is 235.04392 atomic mass units, or AMUs, and then the mass of a neutron is 1.00866 AMUs. Add those two together, you get 236.05258 AMUs. And then the mass of your products, you have the mass for tellurium-137 being 136.92532. The mass of zirconium is 96.91095, and then you have 2 neutrons on that side, so it's 1.00866. And you add all of those together, you'll get 235.85359. So to get the mass loss, you want to subtract the mass of the reactants from the mass of the products. And when you do that, what you get for your mass loss is 0.19899 AMU. And notice we've moved from 1, 2, 3, 4, 5, 6, 7, 8 significant figures for that mass of uranium, for example, to now 5 significant figures. So that's what you're going to consider when you do your E equals mc squared calculation. So that's the next step. Before you plug in your mass to the E equals mc squared equation, AMUs has to be in kilograms, and you'll see why that is in a minute. So to convert AMUs to kilograms, you have to know that there are 1.66054 times 10 to the negative 27 kilograms in 1 atomic mass unit. So that's going to give you 3.30431 times 10 to the negative 28th kilograms. So now you plug things in to the E equals mc squared equation. So your mass is 3.30431 times 10 to the negative 28 kilograms, and the speed of light is going to be 2.9979 times 10 to the 8th meters per second, and that term is squared. What you're going to get there is 2.9697 times 10 to the negative 11, and the units are going to be kilogram meters squared per second squared, which is actually equal to a joule. So your answer is 2.9697 times 10 to the negative 11th joules of energy are released.